let's run through this. The first thing we need to identify is the what? The domain. In this case, our domain goes from minus infinity to infinity. The next thing we need to find are the zeros. So to do that, we're going to set f of x equal to 0. That happens when x e to the minus x equals 0. That happens when either x equals 0 or e to the minus x equals 0. But what?
E to the minus x.
Yeah, e to the minus x is an exponential function, right? And when you raise things to powers, you never get 0. So this never happens. So this is our only 0. Okay. Questions on that, folks? Okay. This is a little bit redundant. In this case, it's redundant. What do we need to go find? Next. We need to find the y-intercept. How do I know I can find the y-intercept? Because I've identified the domain, right? Right. So that you could do these in different order, but I did pick the order that minimizes the redundant work you do. Okay. So we said that 0 is in the domain, so then we can find the y-intercept by evaluating f of 0, which we've already said is 0, 0. Give me thumbs up, thumbs down, thumbs sideways. How are we feeling about this? Stephanie, how are we feeling about this? Okay? Emma? Okay. Okay? All right. Okay. In this case, like the last one, we had no vertical asymptotes or holes. Folks, I can only do so many of these. Will you likely have one that has vertical asymptotes and holes? Yes. And you saw how to encounter that. I had you watch the video of e to the 1 over x for your pre-work, right? That one had both a vertical asymptote and a hole at 0. Okay. All right. So now let's look at the long-term behavior. Okay. This is why I had to wait until today to do this graph. So for the long-term behavior, we want to look at the limit as x approaches infinity of x e to the x. Well, what's the factor of x approaching? Oops, I'm sorry, I dropped the minus thing. What's the factor of x approaching here? Infinity. What is e to the minus x approaching? Okay. So that depends. What does the graph of e to the x look like, folks? The graph of e to the x looks like this, right? So then the graph of e to the minus x is going to look like this. What happens as I go far to the left on the graph of e to the minus x? My y values get closer and closer to? As I go far to the right, excuse me, I pointed my left as I was doing it. As I go far to the right, it's approaching 0. So this has indeterminate form, 0 times infinity, or well, in this case, infinity times 0. Right? That has the indeterminate form, infinity times 0. Can I evaluate that limit? No, I can't. It's a tug-of-war match. Who's going to win? So what do we need to do? We need to go, first of all, rewrite it as a quotient. Which one should I take below the line here? I think there's a real natural choice for which one to take below the line.
E to the negative x.
Yeah. So we take e to the negative x below the line. Careful, it becomes e to the x. Everyone notice I brought it below the line and I inverted it. When you invert e to the negative x, you get e to the x. Thumbs up, thumbs down. How are we doing on that? Anyone have any questions? All right. So now we can go ahead and apply L'Hopital's rule. Why? Because, oh, I should have said this. This now has indeterminate form, which one? Infinity over infinity. Okay. Folks, I made a big deal. Notice I didn't write equals infinity over infinity. I made a big deal about that in the pre-work videos. All right. So we apply L'Hopital's rule, and we're left with the limit as x approaches infinity of 1 over e to the x. And so what does this limit come out to be? 0. Do you see why we couldn't do this particular graph until today? We needed L'Hopital's rule to explore the long-term behavior. Okay. Now, let's look at the limit as x approaches negative infinity of x e to the x. Oops, x e to the negative x. Let's check the other direction. What is the form of this problem? Well, x is approaching negative infinity. The first factor is approaching negative infinity. What's the second factor approaching? Is it?
Oh, no, plus.
So we're plugging in a large negative number, like negative 100 in for x, so then we have minus a minus 100, right? So this is going to e to a large number, which becomes large. So this has the form negative infinity times infinity. I'm not calling this an indeterminate form, right? Everyone notice that? I'm not saying this is indeterminate. What is a large positive number times a large negative number? It's a large negative number. So that limit is not one that L'Hopital's rule applies to, but nor is it one that we need L'Hopital's rule for. It's just a structure. A large number times a large negative number is large negative. There's no ambiguity there. Every time you have a large positive times a large negative, the result is a large negative. So it's not an indeterminate form. Indeterminate form means different times you do it, you get different answers.
But if you were to have like a large number subtracted from the large number.
That is an indeterminate form, infinity minus infinity. We'll learn how to deal with that in another class, in another section. Okay. So folks, the next thing we want to do is build our chart. Okay? So we're going to take f prime of x. Okay? So let's see here. We get the first times the derivative of the second plus the second times the derivative of the first. So that leaves us with 1 minus x e to the minus x. So we get a critical number where? At x equals 1. That's the time when the derivative is 0. Okay, the derivative is always defined. Okay, that was the first derivative. Any questions on that? I did that a little bit fast. Did the product rule, factored out e to the minus x. Okay, everyone okay with that? Okay. Let's take the second derivative. Okay, I think I remember how this train goes, but if you don't believe me, let's see here. Here's the first. First times the derivative of the second plus the second times the derivative of the first. So, we end up with 2 minus x e to the minus x. Okay? So we've got a critical number at x equals 2. So now we're going to build our chart. On our chart go any boundary points or exclusions in the domain, okay, or critical numbers. X minus 2. Sorry about that, folks. Or what goes on my number line here? The critical numbers in this case, 1 and 2. Okay. I think it's still positive 2. Yep, that's all right. That's all right. Good check. Okay, so we're going to pick some test points. What should we pick? Let's pick 0. Let's pick 3 halves, and let's pick 3.
Yeah, what you do?
So then we're going to look at f prime of our test point. So we're going to plug 0 into the first derivative. If I plug 0 into this first derivative, that first factor there is positive. If I plug 0 into the second factor, I'm always going to get positive, right? So we are increasing. And if I plug in 3 halves into the first derivative, then we're going to get that we're decreasing. And if I plug 3 into the first derivative, I'm going to get that we're decreasing. Notice what we've shown here. We've shown that this graph has a local maximum at x equals 1. Okay. We're going to plug these into the second derivative now. So here's my second derivative. If I plug in 0, I get a negative sign, so we are concave down. If I plug in 3 halves, I still get a negative number, so we're still concave down. And if I plug in a 3, we are then concave up, and I've shown that x equals 2 is an inflection point. Because it's in the domain, yes. So these were up here because they were critical numbers. And that is something to always be checking for. All right, we're ready to put it all together. We put the 0 on here. There it is at 0. We put the y-intercept on there. Well, there it is as well. We have no vertical asymptotes or holes to account for. Okay. We do have a long-term behavior of approaching infinity, or excuse me, approaching 0 as we go far to the right. We're not really sure whether we're above or below the line yet. But as we go far to the left, we're approaching negative infinity. That's from our long-term behavior. You don't have to put those arrows on now, but they kind of help you anticipate what's going to happen. Okay. Then we said at x equals 1, we've got a local maximum. So we need to go find the ordered pairs of that local maximum. Well, we would have to find f of 1, right? Which would be 1e to the minus 1, right? But that's the same thing as 1 over e, right? And that's what I gave you a decimal approximation of. I said that 1 over e is approximately 3.68. Oh, 0.368. Okay. So here we are at 1 and then 0.368. I'm going to exaggerate that slightly just so I can fit my inflection point on there as well. Okay. That's 1 comma approximately 0.368. And then we've got an inflection point at 2. Okay. And if you plug 2 into this function, you get approximately, what did I say?
0.217.
0.217? Is it 17 or 71?
7-1.
Okay, folks, we're now ready to put it all together. In that we're heading towards this local maximum at 1. We're increasing in a concave down manner. We then arrive at 1. We continue in a concave down manner, but now we're decreasing. And then we hit this inflection point where we shift to decreasing in a concave up manner. Okay? Folks, how do I know that I don't dip below the x-axis? I know that for 2 different reasons at least. One is because that's the x-axis. How do I know I don't dip below it? Because I would have found another 0. And I only found 1. But another reason why I didn't dip below is, let's look what happens. Suppose you incorrectly dip below. What would you have to do to get back to your horizontal asymptote? You'd have to start increasing, and what would that give you? A local min, and you found all local mins. So that's why we do everything in this order. Okay. All right, folks, sorry to run long on you. If you have questions, I will stick around and answer them as long as you've got them. Thanks for being patient.